Is our understanding of the universe just a drop in the ocean? How do black holes challenge our fundamental concepts about the meaning of space and time? These are the types of questions that transform our perspective from mere curiosity to a whole new level. Today, I will guide you into an exploration structured around 4 critical aspects of modern science that challenge our conventional views: general relativity, quantum mechanics, black holes, and the hypothesis of alien life. Each of these topics is not only interconnected with the others, they also will expand your mind as never seen before. Here we go. In this video, we are guided by the work of Dolores, whose pioneering efforts to investigate the extraordinary have left a mark on the scientific and metaphysical communities. Through her extensive writings, particularly in the convoluted universe, she has provided us with a platform from which we can view the physical and the metaphysical with equal importance. We begin our discussion on general relativity, a theory that redefines the interaction between space and time. Introduced by Albert Einstein in 1905, this theory suggests that the structure of the universe is not static, but rather dynamic, bending and deforming under the weight of mass and energy. The implications of this are profound, influencing everything from the orbits of planets to the propagation of light from distant stars. So, when we talk about quantum mechanics, it reveals the peculiar behavior of particles on unimaginably small scales. Here, reality operates under rules that defy classical logic, suggesting that particles can exist in multiple states simultaneously and even influence each other instantaneously over vast distances. Which brings us to the heart of darkness, black holes. These are not just points of no return, but possibly portals to other universes or historical archives encoded in their event horizons. The possibility of alien life invites us to consider not only the existence of life beyond Earth, but also the forms that life might take, encouraging us to look beyond our solar system and even our galaxy to contemplate communication and interaction with civilizations that may have navigated the vast universe millennia ago. Before we unravel all these mysteries, I invite you to subscribe to our channel, where we always explore interesting and unknown stories in a clear and easy-to-understand way. In the 1970s, Stephen Hawking revolutionized our understanding of black holes with a surprising discovery. Contrary to the long-held belief that nothing can escape a black hole, he demonstrated that they emit radiation, which has profound implications for the destination and information within it. This phenomenon, now known as Hawking radiation, suggests that black holes gradually lose mass and eventually evaporate, raising a significant question. What happens with something that falls into a black hole? Traditionally, general relativity suggests that any matter or information swallowed by a black hole is irretrievably lost to the outside universe. However, the concept of Hawking radiation introduces a paradox. If black holes can evaporate, the information they contain must go somewhere. It cannot simply be destroyed, as this would violate the principle of quantum mechanics that must be conserved. This leads to the puzzle of black hole loss, which has become a central focus in theoretical physics. The dilemma unites general relativity and quantum mechanics, 2 pillars of modern physics that are fundamentally in conflict. While general relativity deals with the macroscopic scales of stars and galaxies and describes gravity as the curvature of space-time caused by mass, quantum mechanics explains the universe on microscopic scales, where particles act on probabilities and uncertainties. Most physicists believe that information lost in black holes is not destroyed, but is somehow encoded in Hawking radiation. However, how the interior of a black hole could be transferred to this radiation remains a major unresolved question in physics. Observationally, detecting this radiation remains a formidable challenge. It is emitted by large black holes such as Sagittarius A at the epicenter of our galaxy and is incredibly faint due to its immense mass and correspondingly low temperature. Smaller black holes would emit more detectable radiation due to their higher temperatures, but none have been found close to Earth. Technical and observational obstacles mean that for now, these theories remain largely in the domain of theoretical physics. The nature of reality is even stranger and more complex than we imagine. Originally conceptualized by physicists Gerard 't Hooft and Leonard Susskind, and later rigorously developed through Juan Maldacena's correspondence, this principle suggests a radical idea. All information contained within a certain volume of space can actually be represented at that boundary. At its core, the holographic principle arises when dealing with the black hole paradox. The reconciliation of these two theories through this principle proposes that information is not lost, but rather encoded in the event horizon. This encoding suggests not in 3 dimensions, but in 2, effectively acting as a holographic image. This principle was significantly advanced by the work of Maldacena in the late 1990s. His theory proposed an equivalence between an n-dimensional quantum field theory and an n+1 dimensional theory of gravity. This concept implies that a gravity-free lower-dimensional universe can cast a holographic shadow on the higher one. The most surprising aspect of this theory is that our 3-dimensional experience could itself be a holographic projection of a 2-dimensional boundary. That totally blows our minds, right? According to the holographic principle, the entropy of a black hole, which is a measure of its information content, is proportional to the area. This discovery implies a maximum density beyond which begins to collapse. The principle also has implications for understanding evaporation, a process in which black holes lose mass and emit radiation, as theorized by Hawking. If it's encoded on its surface, as it evaporates, that could theoretically be released into the universe, suggesting a mechanism by which escapes, thus preserving quantum coherence. In this view, space-time is not a fixed setting, but a dynamic entity that changes and responds to the presence of energy and matter. The flexible nature of space-time, as suggested by general relativity, and the uncertainty inherent in quantum mechanics imply that even the concept of a fixed location in space-time is fundamentally confusing. If our perceived 3-dimensional world is just a holographic projection of a 2-dimensional surface, what does that say about the nature of consciousness and reality itself? Are we, as observers, also part of a complex projection? Traditionally, black holes have been associated with singularities, points where space-time curves infinitely and known physics collapses. However, the singularity within a black hole is not a location in space, but rather a moment in time, a point in the future, similar to the theoretical concept of the Big Crunch. This makes the interior of a black hole a dynamic environment, not a static one, where space-time becomes increasingly distorted until it reaches the singularity. The flow of time inside a black hole also defies our understanding. Time moves at a consistent pace from the perspective of any local observer, whether inside or outside. However, due to gravitational time dilation, an outside observer would see time slowing down near the horizon of these events, eventually appearing to stop. This principle suggests that all information about a 3-dimensional space can be thought of as encoded in a 2-dimensional boundary. If all is inside a black hole is encoded, this challenges our notions of location and volume as defining aspects of storage and entropy. If future discoveries reveal that black holes can function as portals to other universes, or are instrumental in creating new universes, it would radically alter our understanding of the universe. Such discoveries would suggest that black holes are not just endpoints of matter, but also crucial portals or junctions in the structure of space-time. In our recent theoretical explorations, we have ventured into the implications of this principle for neutrinos, particularly how their behavior could potentially validate or challenge our existing models of physics. Neutrinos, often called ghost particles, are known for their elusive nature, barely interacting with matter despite being one of the most abundant particles in the universe. Because of the peculiar properties dictated by the holographic principle, we propose that neutrinos traveling from distant galaxies may gradually lose their identity, transforming into other types of neutrinos or dissipating their energy in ways not normally predicted by standard quantum field theory. Essentially, if neutrinos are not perfectly orthogonal, their paths through the universe become entangled with various quantum states, leading to a likelihood of transformation or disappearance over vast distances. Our experiments aimed to observe this phenomenon using the ice cube detector in Antarctica, an installation designed to detect it is intrinsic, capturing the faint flashes they produce when they interact with the ice. Ice Cube exploits the clarity and density of deep Antarctic ice to monitor high-energy neutrinos, which can reveal interactions occurring at the most fundamental levels of matter. As neutrinos from distant galaxies travel toward Earth, those with sufficiently high energies would exhibit a significant drop in detectability, corresponding to the energy levels where holographic effects become pronounced. Interestingly, our observations at IceCube showed a cutoff in the detection of high-energy neutrinos that lines up suspiciously well with our predicted energy levels. However, the accuracy of this cutoff is limited by the limits of current experimental technologies, since detector sensitivity decreases precisely where our theoretical cutoff occurs. Dark matter and dark energy are fascinating because they are predominantly relevant in scenarios where gravitational forces are extremely weak. This is somewhat counterintuitive, since new physics typically emerge under conditions of strong, not weak, interaction. Dark energy manifests its effects later in the timeline, becoming significant only as the universe expands and the density of matter decreases. At first, this energy was irrelevant compared to matter and radiation. Its constant density over time means that as the universe expands, dark energy dominates, influencing the acceleration of the universe during these expansive dilute phases. On the other hand, dark matter becomes noticeable in the outer regions of galaxies, where the density of ordinary matter decreases. Within these regions, the gravitational attraction of visible matter is sufficient to explain the observed dynamics. However, at greater distances from the center, where the gravitational influence of visible matter decreases, the presence of matter becomes essential to explain the observed rotational speeds and gravitational effects. Hugh Everett's Many Worlds interpretation, MWI, of quantum mechanics proposes a radical rethinking of quantum phenomena and their implications for reality as we understand it. At the heart of MWI is the idea that all possible outcomes of quantum measurements are physically realized, each in a different world or branch of reality. This leads to a universe made up of a vast or potentially infinite number of parallel worlds, each representing different outcomes of all quantum processes. According to Everett, when a quantum measurement is made, the universe divides into a number of parallel existences equal to the number of possible outcomes of that measurement, with each outcome occurring in its own newly created world. These worlds are complete and non-interacting, each being a complete version of the universe containing a version of us observing one of the possible outcomes. This division of worlds happens every time a quantum measurement is made, leading to an ever-increasing number of parallel universes. One mistake is the physical spatial location of these parallel worlds. In Everett's theory, these worlds do not exist in a physical space like our universe. Instead, they exist in a high-dimensional Hilbert space, which is the mathematical space of all possible quantum states. In this sense, the space where these worlds exist is entirely abstract and is not limited by physical conceptions of space as understood in classical physics. The challenge of visualizing the many worlds of the MWI lies in the abstract nature of quantum mechanics itself. These worlds are not spatially separated. They are spread out by the wave function in Hilbert space. This wave function contains all possible states of the universe, with each world representing a different configuration of particles and fields according to the results of all quantum events. The fact that these worlds do not interact with each other is due to the decoherence process, which effectively isolates each world, avoiding quantum superpositions between them. While it offers a mathematically consistent interpretation that eliminates some of the paradoxes of quantum mechanics, it also requires a radical expansion of our concept of reality. If our universe were a simulation, this would imply that what we perceive as our physical laws and constants could simply be parameters set by the computing system of an advanced civilization. When it comes to creating simulated realities, humanity's technological trajectory suggests that increasingly complex virtual environments are likely to be developed in the future. These simulations, enhanced by advances in artificial intelligence and computing power, could offer experiences indistinguishable from our perceived reality. Such developments would not only revolutionize entertainment and education, but could also provide profound insights into human psychology, sociology, and the development of artificial consciousness. Philosopher David Chalmers has argued that entities within these simulations could have experiences as valid as those in base reality, suggesting a form of digital consciousness. However, the technical challenge of creating a fully immersive simulation that accurately mirrors the complexity of the universe, or even human consciousness, is immense. Current technologies and understanding of the brain and the universe are primitive compared to the requirements of such a feat. The discussion extends to the domain of AGI, where misconceptions abound regarding the proximity of current technologies to achieving human-like intelligence in all domains. AGI remains a theoretical concept rather than an imminent technological reality, in large part because intelligence involves more than processing power or data. It requires understanding, adaptability, emotional engagement, and ethical reasoning, among other complex characteristics that are difficult to understand. The interplay between entropy, complexity, and the laws of thermodynamics, we discover a fascinating perspective on the universe and our place in it. Far from combating the forces of entropy, life and complexity thrive because of them. Our existence, similar to surfing waves of increasing entropy, depends on this fundamental principle to maintain stability and evolve. It challenges us to look beyond increasing entropy and consider how structures and systems emerge over time. This approach does not only apply to physical systems, but also extends to biological and cognitive processes, where complexity manifests itself in the system's ability to use information effectively. The possibility of alien life emerges as a tantalizing question at the intersection of astrophysics, biology, and philosophy. The universe is immensely vast, with billions of galaxies, each home to countless stars and potentially habitable planets. Given the enormous scale of the universe and the repeated demonstration of the resilience and adaptability of life on Earth, the hypothesis that life exists elsewhere seems not only plausible but also likely. The search for extraterrestrial life is fueled by the discoveries of exoplanets in the habitable zone, regions where conditions could allow the existence of liquid water, a crucial ingredient for life as we understand it. Advances in astrobiology, the study of the potential for life in the universe, continually refine our understanding of where and how life could thrive. Furthermore, the study of extremophiles on Earth, organisms that thrive in environments previously considered uninhabitable, expands our perspective on possible life forms in the universe. These organisms challenge our Earth-centered view of life, suggesting that life could exist under conditions very different from those on our planet. Are we alone, or is the universe teeming with life each civilization rising and falling in its own corner. The search for alien life also reflects our search for a deeper understanding of how life began on Earth and what conditions are essential for its emergence. Missions like the James Webb Space Telescope and other future explorations aim to analyze the atmospheres of distant exoplanets, looking for signs of biosignatures. Meanwhile, initiatives like SETI, Search for Extraterrestrial Intelligence, probe the universe for signs of other civilizations. Based on our knowledge of the universe and the tenacity of life within it, the laws of probability and scientific investigation support this hypothesis of alien life. Each discovery in this field brings us closer to understanding the potential for life beyond Earth. Whether or not we find other life forms, this quest deepens our appreciation of life on Earth and drives us to continue exploring the unknown.